If our universe truly exists within a black hole, it raises profound questions about our ultimate fate. Black holes are known to evolve over time, slowly evaporating due to a process called Hawking radiation. If our universe is within one, does that mean it too will one day vanish as the black hole dissipates? Or could there be an escape, some kind of cosmic rebirth that leads to an entirely new existence? Some physicists theorize that black holes could act as cosmic recycling centers, where matter and energy are not lost but transformed. If this is the case, our universe might one day emerge into a larger, more complex reality beyond our current comprehension. This could mean that what we perceive as the Big Bang was actually the moment our black hole parent universe collapsed, birthing our reality from the remnants of another. Another mind-bending possibility is that time itself behaves differently inside a black hole. Could it be that from an outside perspective our universe is frozen in time, while from within, billions of years pass as we perceive them? This would suggest that the very fabric of time and space is relative, shaped by the black hole that contains us. Future scientific advancements such as quantum gravity theories and deeper explorations of black hole physics may one day provide more definitive answers. Until then, the idea that we exist inside a black hole remains a tantalizing hypothesis, one that challenges our perception of reality and the very nature of the universe. If we are part of an infinite chain of black holes birthing new universes, then our search for ultimate truth may never end. Instead, it could be an eternal journey, one where every discovery leads to new mysteries, forcing us to question not just where we are, but what we are in the grand cosmic scheme. Pluto was regarded as a legitimate planet in our solar system and remains a compelling and perplexing dwarf planet, placed distant from Earth despite its former classification. Recent daring remarks by respected astrophysicists Neil deGrasse Tyson and Michio Kaku have stirred new interest in Pluto. They have suggested that Pluto's frozen world could be on a trajectory toward a catastrophic collision with Neptune, prompting a flurry of questions about the plausibility and consequences of such an event. Could this scenario be an exaggerated theory, or is there a legitimate cause for concern? Let's study the potential repercussions of a Pluto-Neptune collision. Initially classified as a planet, Pluto was recategorized as a dwarf planet due to its erratic orbit, and this decision has kept it a subject of ongoing discussion in astronomy circles. The latest studies by leading scientists reveal that Pluto's orbital path dangerously overlaps with Neptune's, generating alarm about. The latest studies by leading scientists reveal that Pluto's orbital path dangerously overlaps with Neptune's, generating alarm about the potential risks of a future collision. However, astronomers reassure that while their orbits do cross, the gravitational interactions between the two bodies, particularly with the influence of Neptune's larger mass and Pluto's resonance with it, make an actual impact highly unlikely in the foreseeable future. Despite these reassurances, the mere possibility of such an event sparks curiosity about the consequences. If Pluto were to collide with Neptune, the impact would be catastrophic, potentially altering Neptune's atmosphere, its ring system, and even affecting the gravitational balance of the outer solar system. Debris from such a collision could create new celestial bodies or even disrupt the orbits of nearby moons and objects in the Kuiper belt. This ongoing debate highlights the dynamic and ever-evolving nature of planetary science. As research continues, scientists remain committed to understanding the complex gravitational mechanics that govern our solar system, ensuring that we are prepared for any cosmic surprises that may arise. Beyond the immediate aftermath of a potential Pluto-Neptune collision, scientists speculate on the long-term implications for the solar system. Such an event could send shockwaves through the Kuiper belt, dislodging other dwarf planets and icy bodies, potentially sending them toward the inner solar system. This could lead to an increased number of asteroid and cometary impacts on planets like Earth, Mars, and Jupiter. Additionally, the loss or alteration of Pluto could have unforeseen effects on Neptune's gravitational stability. Though Neptune is significantly more massive, a drastic change in its surroundings could subtly influence its own orbit and that of its moons, such as Triton, which is already believed to be a captured Kuiper belt object. Despite these theoretical concerns, the prevailing consensus among astronomers is that Pluto and Neptune's orbital resonance, a stable gravitational relationship that keeps them from colliding, will continue to protect them from such a fate. However, continued observations and advances in astrophysical modeling will be necessary to refine our understanding of these distant celestial bodies. Ultimately, Pluto remains a fascinating world, whether as a potential collision threat or as an enigmatic dwarf planet on the fringes of our solar system. Ongoing exploration missions, such as potential follow-ups to NASA's New Horizons, may provide more insights into Pluto's composition, atmosphere, and long-term orbital dynamics. Until then, the debate over Pluto's fate and status will continue to captivate both scientists and the public alike. The fascination with Pluto extends beyond its potential collision risks. Scientists are increasingly interested in its unique characteristics, including its complex geology, thin atmosphere, and the possibility of an underground ocean. Data from NASA's New Horizons mission revealed surprising details about Pluto's surface, such as towering ice mountains, vast nitrogen plains, and evidence of cryovolcanism, geological activity driven by the freezing and melting of volatile substances like water, methane, and nitrogen. These discoveries raise compelling questions about Pluto's internal structure. Some planetary scientists hypothesize that beneath its frozen crust, Pluto may harbor a subsurface ocean, similar to those suspected on Jupiter's moon Europa and Saturn's moon Enceladus. If true, this could have profound implications for astrobiology, as liquid water is a key ingredient for life. Could Pluto, once dismissed as a barren, icy rock, actually harbor conditions suitable for microbial life? Furthermore, Pluto's largest moon, Charon, adds another layer of intrigue. The Pluto-Charon system is unique because the two bodies are tidally locked to each other, meaning they always show the same face as they orbit a common center of mass. This binary relationship suggests a fascinating history of planetary evolution, possibly involving a giant impact similar to the one that formed Earth's moon. Looking ahead, astronomers and space agencies are considering new missions to revisit Pluto and explore the Kuiper Belt in greater detail. While New Horizons provided a brief flyby, future spacecraft could conduct extended observations, orbit the dwarf planet, or even deploy landers or probes to investigate its surface and interior. Such missions would deepen our understanding of Pluto and the outer solar system, shedding light on the processes that shaped our cosmic neighborhood. Despite its reclassification as a dwarf planet, Pluto remains a subject of scientific and public fascination. Whether as a potential impactor, a possible host of hidden oceans, or a gateway to understanding the early solar system, Pluto's mysteries continue to challenge and inspire our quest for knowledge about the universe. As interest in Pluto grows, discussions about future missions to the distant dwarf planet have gained momentum. Scientists and space agencies are exploring possibilities for a Pluto orbiter, which could provide long-term observations of its climate, surface changes, and potential subsurface ocean. Unlike the fleeting flyby of New Horizons, an orbiter would allow for detailed mapping, atmospheric sampling, and even seismic studies to probe Pluto's internal structure. One proposed mission concept, tentatively named Persephone, envisions a spacecraft that would reach Pluto in the 2040s. Equipped with advanced instruments, it could study Pluto's potential geologic activity, assess its ice composition, and search for signs of subsurface water. Additionally, it could explore the dynamics of Pluto's thin atmosphere, which expands and contracts as it moves along its elliptical orbit. Understanding these changes could provide valuable insights into how similar icy worlds evolve over time. Beyond Pluto, the Kuiper Belt as a whole remains a largely uncharted frontier. This vast region, extending beyond Neptune, is home to thousands of icy bodies, some of which may hold clues to the early solar system's formation. Missions targeting other Kuiper Belt objects, KBOs, could reveal whether Pluto is unique or if similar processes are occurring on other distant worlds. The discovery of additional moons, unusual surface features, or even active geological processes in this region could revolutionize our understanding of planetary science. The debate over Pluto's planetary status also continues to spark discussions within the scientific community. Some astronomers argue that Pluto's complex geology, active surface, and atmospheric processes make it more planet-like than previously thought. They suggest that the International Astronomical Union's (IAU) 2006 decision to reclassify Pluto as a dwarf planet should be reconsidered. Others, however, maintain that the distinction is necessary for scientific clarity, especially as more Pluto-sized objects are discovered in the Kuiper belt. Regardless of its classification, Pluto remains one of the most fascinating celestial bodies in our solar system. Its mysteries challenge our understanding of planetary formation, orbital mechanics, and even the potential for life in extreme environments. As technology advances and new missions become feasible, the next few decades could bring remarkable discoveries about Pluto, the Kuiper belt, and the outer reaches of our cosmic neighborhood. For now, Pluto stands as a symbol of curiosity and exploration, an icy world on the edge of our solar system, waiting for future generations to uncover its secrets. As Pluto continues to captivate scientists and space enthusiasts alike, discussions extend beyond its planetary classification and orbital dynamics. One of the most intriguing aspects of Pluto's existence is its role as a window into the past, a frozen relic from the early solar system that could provide invaluable clues about the formation of planetary bodies. Pluto as a time capsule of the early solar system. Unlike the terrestrial planets or gas giants, Pluto and other Kuiper belt objects, KBOs, have remained largely unchanged for billions of years. These icy worlds serve as cosmic time capsules, preserving the chemical composition and structural features of the primordial nebula that formed our solar system. By studying Pluto's surface, atmosphere, and interior, scientists can gather data on the conditions that existed in the outer solar system during its infancy. One of the key questions surrounding Pluto is its internal heat. Despite being located in one of the coldest regions of the solar system, evidence suggests that Pluto has experienced geological activity in its past, and possibly even in the present. The presence of massive ice mountains, flowing glaciers of nitrogen, and possible cryovolcanic features hints at an internal heat source. This raises speculation that radioactive decay or tidal interactions with Charon may generate enough heat to sustain a subsurface ocean. The possibility of subsurface oceans and habitability. The idea of an ocean beneath Pluto's icy crust is particularly exciting for astrobiologists. If liquid water exists beneath the surface, it could create an environment capable of supporting microbial life, similar to the suspected underground oceans of Europa and Enceladus. The presence of organic compounds detected on Pluto's surface further fuels speculation about its astrobiological potential. While the extreme cold and lack of sunlight make surface life highly unlikely, the possibility of life thriving in a deep, insulated ocean remains an open question. Future missions could test this hypothesis by deploying ice-penetrating radar to map the subsurface structure, or by analyzing the chemistry of Pluto's surface for signs of water exchange with the interior. If Pluto does have an active subsurface ocean, it could redefine our understanding of habitability in the outer solar system, expanding the list of worlds that could potentially harbor life. The future of Pluto exploration. As technological advancements make deep space exploration more feasible, several mission concepts have been proposed for revisiting Pluto and its surrounding environment. 1. Pluto Orbiter and Lander. Unlike New Horizons, which conducted a brief flyby, an orbiter would allow for long-term observations of Pluto's surface, atmosphere, and potential geological activity. A lander could collect surface samples to analyze their composition up close. 2. Kuiper Belt Explorer. A mission that extends beyond Pluto to study other large Kuiper belt objects could provide valuable comparisons, helping scientists determine whether Pluto is unique or part of a broader class of dynamic icy worlds. 3. Ice-penetrating probe. If Pluto's subsurface ocean is confirmed, a probe designed to drill or melt through its thick ice layer could be a game-changer for astrobiology, similar to concepts proposed for Europa and Enceladus. These ambitious missions may still be decades away, but they represent the next logical steps in unraveling Pluto's mysteries. In the meantime, ground-based telescopes and future space observatories will continue to monitor Pluto, tracking its atmospheric changes and its long elliptical journey around the Sun. Conclusion. Pluto, once dismissed as just another distant rock, has emerged as one of the most fascinating objects in the solar system. Whether it is studied as a potential impact threat, a geologically active world, or a possible host for subsurface life, Pluto remains a focal point of scientific curiosity. With every new discovery, we move closer to understanding not only this icy dwarf planet but also the broader forces that shaped our solar system. As humanity continues its exploration of space, Pluto serves as a reminder that even the most distant and overlooked worlds can hold the greatest secrets, secrets waiting to be unlocked by the next generation of explorers. The ongoing debate: Pluto's planetary status. Despite the wealth of new information about Pluto, debates over its classification continue to spark controversy among astronomers and the public. The 2006 decision by the International Astronomical Union (IAU) to demote Pluto to a dwarf planet was based on 3 criteria for defining a planet. 1. It must orbit the Sun. 2. It must be massive enough for its gravity to pull it into a roughly spherical shape. 3. It must have cleared the neighborhood around its orbit. Pluto meets the first 2 criteria but fails the third, as its orbit overlaps with Neptune's and is populated with other Kuiper belt objects. However, some planetary scientists argue that the definition is too restrictive and that Pluto's complex geology, atmosphere, and potential subsurface ocean make it more deserving of planetary status than some of the moons in our solar system, such as Titan or Ganymede. In recent years, planetary scientists such as Dr. Alan Stern, the principal investigator of New Horizons, have pushed for a broader definition of planets, one that would reinstate Pluto and recognize many other large, geologically active bodies in the solar system as planets. While the IAU has not formally reconsidered Pluto's status, public fascination and ongoing scientific discoveries continue to fuel the debate. Pluto's role in understanding exoplanets. Interestingly, Pluto's study has implications far beyond our solar system. With the discovery of thousands of exoplanets orbiting distant stars, astronomers have identified numerous Pluto-like worlds, small icy bodies that challenge traditional notions of planetary classification. Understanding Pluto's atmosphere, surface composition, and internal heat sources could provide valuable insights into similar exoplanets, especially those located in their star's habitable zone. Some exoplanets, known as super-Plutos, are significantly larger than Pluto but share its icy composition and possible subsurface oceans. Studying Pluto could help scientists predict the conditions on these distant worlds and assess their potential for supporting life. The cultural and scientific legacy of Pluto. Beyond the scientific community, Pluto has held a special place in human culture. From its discovery by Clyde Tombaugh in 1930 to the excitement surrounding the New Horizons flyby in 2015, Pluto has captured the imagination of generations. Its demotion to a dwarf planet sparked public outcry, with many people refusing to accept the change, and even led to humorous campaigns and petitions calling for its reinstatement. Pluto has also inspired literature, film, and music, often symbolizing the mysterious and uncharted frontiers of space. The phrase Plutoed even became a verb, meaning to demote or devalue something unfairly. The road ahead. With each passing year, Pluto continues to remind us that there is still much to learn about our solar system's outer reaches. Whether through new missions, advances in telescope technology, or breakthroughs in exoplanet research, Pluto's story is far from over. As humanity ventures deeper into space, it is only a matter of time before we return to Pluto, unlocking more of its secrets and redefining our understanding of what it means to be a planet. Until then, Pluto remains a testament to scientific curiosity, resilience, and the ever-evolving nature of knowledge. Neptune's. At certain points during its long journey around the Sun, the gravitational forces exerted by Neptune and other planets have played a significant role in stabilizing Pluto's orbit, ensuring it remains relatively constant over centuries. Despite this, predicting the future behavior of celestial bodies remains a complicated and unpredictable task. Neptune's. At certain points during its long journey around the Sun, the gravitational forces exerted by Neptune and other planets have played a significant role in stabilizing Pluto's orbit, ensuring it remains relatively constant over centuries. Despite this, predicting the future behavior of celestial bodies remains a complicated and unpredictable task. As astronomers refine their models and improve observational techniques, our understanding of planetary interactions continues to evolve. The intricate dance of gravitational forces within the solar system influences not only Pluto but also countless other objects in the Kuiper belt and beyond. These subtle but persistent gravitational nudges shape the long-term dynamics of celestial bodies, sometimes leading to orbital shifts, resonances, or even ejections from the solar system. Future space missions and advanced telescopes will further enhance our ability to map these cosmic interactions, allowing scientists to predict planetary movements with greater accuracy. Yet, even with modern advancements, the complexity of multi-body gravitational interactions ensures that a degree of uncertainty will always remain in celestial mechanics. As our understanding of celestial mechanics deepens, astronomers continue to uncover new insights into the delicate gravitational balance that governs planetary and satellite motion. The study of Pluto and Neptune's relationship provides a fascinating glimpse into the broader dynamics of orbital resonance, a phenomenon that extends far beyond our solar system. Resonances like the one between Neptune and Pluto are not unique. Similar gravitational interactions have been observed in exoplanetary systems, influencing planetary orbits and even the potential habitability of distant worlds. Scientists believe that these gravitational forces may have played a crucial role in shaping the early solar system, guiding the migration of gas giants and scattering planetesimals into their current configurations. As technology advances, future space telescopes and interplanetary probes will allow for even more precise measurements of these cosmic forces. Missions like the James Webb Space Telescope and upcoming deep space observatories will provide unprecedented data on planetary atmospheres, compositions, and orbital patterns. Meanwhile, robotic missions to the outer solar system could help unravel the mysteries of trans-Neptunian objects, shedding light on the formation and evolution of distant celestial bodies. Despite these advancements, the long-term stability of our solar system remains a subject of debate. Tiny perturbations, asteroid impacts, and the cumulative effects of gravitational interactions over millions of years introduce uncertainties that challenge even the most sophisticated models. Still, by studying the intricate gravitational interplay between planets like Neptune and Pluto, scientists move closer to unlocking the secrets of the universe and understanding the grand design that governs celestial motion.